Going live, and we're live. Excellent. We're back. Okay. I haven't updated my calendar here. We have T minus 13 days until we hit that AP test. 13 days until you're sitting in a trailer. It's going to be weird. What's going to be nice, I haven't actually talked about this per se, but after the day after you take the AP test, that morning, obviously, you'll be back in here. It'll be a Wednesday. We'll have 60 minutes. It'll be a half day, that whole thing. Now, it's going to be a little weird after the AP test. I mean, literally, it's the day after the AP test. I would prefer to debrief that particular day after the AP test. And that is mainly what I'm going to be focusing on. But with the time crunch that we have till the end of the year, I will have to begin the process towards the quote unquote, I should probably do this in front of the camera so people could see me, quote unquote, final exam. Because obviously you're not taking an actual test for my final exam, and I won't know what your AP scores are until July. So as I've mentioned in the past, I do have a project lined up for you guys to begin working on. So I do have the pieces put into place that will take us through the end of the year. Just so you guys are aware, obviously with the number of seniors that are in this class, the week of quote unquote senior exams, that's when that particular project would end up being due. And then this week, this is the week of like actual exams, I believe, in which whoever's not a senior, like, I mean, we just play games or something that day or something. I don't know. We'll see what happens. Rig up a video game system or something. I don't know. But clearly, obviously, we're not doing anything that particular week, the week of June 14th. But we'll get there when we get there. Anyway, for those of you in the live chat, if you would be so kind as to leave a comment. I'm just double checking. I just got to get it open on my phone real quick. The actual live chat so I can see, because again, the computer for some reason is not working the way that I want it to. There we go. Good. Next, you have, as I mentioned the other day, a minor. I said that I would either post this thing later on Monday or I would post it on Tuesday. I ended up posting it on Tuesday. It is not due until Friday. I did that specific just so I could make mention of it today in class, of course, again. But that thing is not due until Friday. It is a kind of a small assessment, a couple of questions on chi-squared that you'll be able to knock out. Of course, email me if you have any questions. I am trying to catch up on grades because, lo and behold, progress reports are somehow due on Monday, which is like, this is going to be so weird. Think about it. You got progress reports due May 17th. Then we have that week. Then we have a shortened week. And then we have another shortened week. Then we have senior exams and then final exams. Yeah, but get in all of your assessments and get in all these things and blah, 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 blah. Okay, yes, of course. Anyway, here's my goal for today. We have a shortened period. We're only here till 8:20. I would like to focus today entirely on probability. Based on the quizzes that you guys took last time, I was able to identify a lot of key features within probability that we should go over and we should review. I have a bunch of multiple choice questions set aside that fall into either the binomial camp or another problem area of probability that I would like to go over with you. And of course, I will give you the heads up as to which one is which when we get there. As we're going over these problems, I would like to write down some information in terms of a review. But of course, for some of these problems, not all of these problems, but for some of these problems, you do need a graphing calculator. So I am going to try something here that I haven't really tried yet, and I'm a little hesitant as to how this is going to work. For those of you online, it's not going to affect you. I was supposed to turn in all of my graphing calculators last September, and I thought I did. I put them all in a bag. They said leave them in this spot in the classroom. And for how long has it been since September? October, November, December, January, February, March, April, May. Been 8 months. 8 months, those bags have been sitting right there. I don't know if you noticed them. No? They're literally my calculators. Now, those calculators have been sitting for 8 months. But what I'm going to ask you to do, and I'm going to have you come up one row at a time because I want you to get a little practice with this. Because these are the calculators that you would end up using on the AP test, for the actual written AP test, because you can't use the ones on the computer. I'm going to ask that you all grab a calculator. And then for those of you that are in the classroom, you won't need your Chromebooks. You will have your notebooks and you will have the calculator because I just want to try and get used to it. But I do have these just in case. No one's touched them in 8 months, just for the record. But I'm just trying to be cautious. If you choose to kind of do this then. But then when you return them, then you can like wipe them down actually. So that'd be actually fantastic. Let me actually just get the first one out of here because for some reason this thing kept popping back in. I'll take the first one out. Come on, you. How does this thing even work? There we go. I'll take that one out myself, and I'll put this over here. Cool. So if you guys in the first row, if you want to kind of grab this handheld calculator, that would be fantastic. You can always wipe it down with one of these things right here. That'd be fantastic. Let's do that real quick. For those of you in the live chat, just bear with me for a minute as people get their calculators. Next row, come on, go. Yeah. That's perfectly fine, yes. Well, what version is that? That should work great. Yeah, that should absolutely work great. No one's going to stop you from using that on the AP test, you know. Next row, go get them. Because again, I just want you to get used to this idea of what the handheld calculator is. Yay! Okay, give me 1 second. Okay, I have a couple backup ideas. Number one, this thing. Wait. Which obviously, yeah, I'll take care of that right here. Next row, if you haven't already come up and get them right here. I'll take the dead one. Now, for those of you that have ones that say like low battery and stuff, I'm going to get backup batteries from someone because apparently they don't trust me enough to have all the backup batteries. And then I go through them like candy. So here, I'm going to trade with you. I just like this one better. Oh, you do? Fantastic. Okay. Okay, trade. Oh, put the cap back on it. Or the cover back on it. There we go. And then I'll find out batteries for these. That'd be fantastic. And you all, okay, good. So, for those of you at your seats, you won't need your Chromebooks, but I would ask that you do have those notebooks out and open because I have some problems that I would like to go over with you. Dead too? Okay. Did you get a replacement? No? Okay. So the dead ones leave there. This is good because now, obviously, I don't want you showing up to the AP test with a dead calculator, so this is actually perfect that we're actually going through these. If it's dead, so yeah, put it in that pile. Hi. Well, that's a lot of dead calculators. Is it empty?
I don't know if these are all dead or not.
No clue. Let's give it a shot. Are you kidding me? Oh my gosh. This is fantastic. It is. Okay. So all of these are dead. Fantastic. Okay. I will rectify that. I will put in an order to the office because I don't have any others other than the one at my desk, which I'm using. So I'm going to put all these aside. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh my gosh. 11 calculators. Okay. But yeah, this is actually perfect because, like I said, I need to have replacement calculators. So, okay, I have 11 over there. Now I'm going to do a quick inventory. Please raise your hand if you are holding one of my calculators. Hi. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So 10, and then I have 11 that are dead over there. I'm just trying to make sure I have enough for everybody, is my point. How many people have their own handheld graphing calculator? Just 2 of you? Okay. 3, there you are. You have one at home, though. Okay, that's good to know. That is good to know. Might have one? Okay. We should have just enough then for everybody. If all 25 of you show up on the day of the test, I should have just enough for you. Okay, this is good. Because I pulled out this little box of batteries, and I'm just like, yep, I only have 4 batteries. That's fantastic. Yay. The last thing I need is for you to get to the AP test and have a dead calculator right when you begin. That is the absolute last thing that you need. Oh, there you go. I just got the email about AP testing today. Good, so I have a list. That is good to know. Okay, let's get started. Like I said, I want you to have these, some of these review pieces in your notes. I will show you when I actually do go to my notes. Let me flip this over. Now, some of these problems may look familiar because we may have talked about them in the past. But I want you to see what we got. Now, again, just for the sake of argument, in your own notebook, you can make a note for yourself as to which letter you would have chosen. So you can just keep track for yourself. Yes, I would have gotten that one right, or oh crap, I don't know what I'm doing on this one. But you can still make a guess, because sometimes making a guess, you never know if you're correct or not. So let's start with something like this. I'm going to zoom in, I'll focus the camera. There we go. Come on, you. Suppose 80% of jurors come to a just decision, a fair decision. In a jury of 6 people, what is the probability that more than half come to a just decision? Just for the sake of argument, this is a binomial problem. I'm going to give you a few moments to kind of maneuver that out. I'm going to fix the angle for those online. Now, again, being that we are prepping for the AP test, my job is to help you understand quickly what these questions are asking of you. I said it was a binomial problem. They're giving you this first statement. Suppose 80% of jurors come to a just decision. That is a general statement. That is a population parameter statement, if you would. 80% of jurors come to a just decision, meaning P equals 0.8. And I guess without saying it, they're not actually saying it, but the idea is that, well, from one person to the next, it's always 80% chance. Each person's ability to come to a just decision, it's implied that each person is independent of the next person. But then they go to an actual, no pun intended, a trial of 6 people. It's not that, yeah, anyway. 6 people in a jury. Okay, each of them individually have an 80% chance. What is the probability that more than half come to a just decision? Now, more than half, meaning 50% or more, meaning 3 or more. Oh, wait, no, I'm sorry, not 3 or more than half. Meaning it can't be 3. It has to be more than half. It can't be equal to 3. So in this situation, actually, you know what? I'm going to write this on a piece of paper, actually, in a minute. I'll write this on a piece of paper in a minute. But I'm going to type something in right here. Boom. Let me double check to make sure that I am correct on what I'm saying so I don't look like a fool. But here are my calculations. These are the only calculations that I did to get this answer. And it is correct. There are multiple ways to get this answer, but the answer is D. Now, what is my rationale and reasoning behind why? I want to bring out a piece of paper for my notes. Where is my note? Did I leave that somewhere? Oh, nope, there it is. Good. Today is the 12th. I'm just going to call this probability review. And this is just one of the multiple choice questions that we're covering. So this is the third problem where P equals 0.80 and N is equal to 6. And the question that they want to know, what is the probability of getting greater than 3 in that situation? This is basically representing this situation. Suppose 80% of jurors come to a just decision. In a jury of 6 people, what is the probability that more than half of them come to a just decision? Well, you could have 0, 1, 2, 3, 4, 5, or 6 of them come to a just decision. The question that they're asking is basically, what is the probability of this happening? This is what you're actually looking for. So what I typed in was I did binom CDF parentheses 6 comma 0.80 comma 3, because as you know, when you do binom CDF, whatever this number is, in this case 3, it's going to calculate the probability of getting 3 successes or less. You can't change that binom CDF, unfortunately. But I don't need that. I need 4 or more. So I do a little 1 minus action on there, and it knocks out the appropriate answer. 0.90112, which obviously is the correct answer to this problem. There is a 90% chance that more than half will come to a just decision. Announcement. Now I'm going to throw another problem at you. This one is slightly binomial. I want to be very clear. You're not actually going to do a binom for the next problem, but you may be using binomial aspects to get the problem done. Let me show you this next problem, and I'm going to give you some time to knock it out. 53% of adults say they have trouble sleeping. If a doctor contacts a simple random sample of 85 adults, what is the probability that over 55% will say they have trouble sleeping? You're not actually going to use a binom here, but this problem does have binomial components. I'm going to give you a little bit of time, see if you can knock this one out. Okay. I'll give you the answer, and then I want to talk about how. The answer should be B. You can see that right there. Now, there's a bunch of gibberish right here, but I'm going to show you how you could do this problem in two ways. I'm going to show you how you can do this particular problem in two ways. This is question number 6. They say 53% of adults have trouble sleeping. So P is equal to 0.53. That is the assumed population proportion. A doctor contacts a simple random sample of 85 adults. So the sample size is 85. Then the question is basically saying, okay, what is the probability that you get more than 55% actually experiencing trouble sleeping? You could do this problem in one of two ways. Now, because of all the individual components, it's proportions, you have a large enough sample size, they're randomly selected, 85 adults is less than 10% of the adult population. You could go through all of the assumptions and conditions. You can use a normal CDF here. You can use a normal CDF here. In fact, one of the most straightforward ways of using this normal CDF, your limits would be 0.55, comma, big number, comma, the mean, which in this case is 0.53, that is the generally accepted mean, and the standard deviation, which if you remember with proportions would be the square root of PQ over N, which in this case would be 0.53, 0.47 over 85 square root. I'll show you how to type all of that in one moment. But this is one way of potentially handling this problem. The problem never said anything about being normal, but it can be inferred based on the fact that it's proportions, and you can go through all of those assumptions and conditions. Randomness, independence, large enough sample size, less than 10% of the population. If you wanted to, you could even do expected successes and failures, but you don't have to write any of that out because it's a multiple choice question. So if you do that calculation, and I'll show you that right here, notice how I typed it in. It'll focus in a moment. There we go. Notice how I typed that sucker in. I mean, if you wanted to, you could calculate that standard deviation separately. But either way, it gets you that answer. 0.356 or whatever it is, 0.3558. It would round up, 0.3559. But anyway, that's besides the point. But there is another way of handling this problem. There is another way of handling this problem if you consider it to be binomial. Think back to what the definition of a binomial was. In probability, a binomial is a set number of trials, which in this case is 85, a fixed probability, which is 0.53, meaning it does not change from trial to trial, independence, and you're looking to get a certain number of successes. The other thing you need to know is that as the sample size grows, and I can even put this, as sample size grows, a binomial becomes more normal. As the sample size grows, a binomial becomes more normal. That's why when we did binomials, we were typically thinking like smaller sample sizes. Like, oh, Mr. Markey is one of 4 children. Okay, of those 4 children, what is the probability that my parents would only have 1 boy? That's a binomial. We would not be able to do normal with that because that sample size is so stinking small. But as that sample size grows, the binomial becomes more normal. So I could technically do this. N times P will give me that binomial mean. N times P will give me that binomial mean, which in this case is 45.05. I could do, well, in this case, they want to know 0.55 in this case. So I'm going to have to do, well, I could do N times a little P hat action going on here. I could do 85 times 0.55 to get my limit here, my lower limit, 85 times 0.55. So they're looking at getting 46.75 or more. And if I wanted to get that standard deviation, I would have to multiply out square root of NPQ, which I'll show you what that, well, actually, I'll just type that in actually on the calculator itself, but that would be square root of 85.53.47. Let me figure out what that decimal actually is here. Square root of 85 times 0.53 times 0.47. Boom. It's approximately 4.601. For a multiple choice question, you don't have to write out this stuff. I just want you to be able to see that this is possible. This is absolutely stinking possible. So if you look at it from a binomial point of view, you would do normal CDF, 46.75, comma, some big number, comma, the accepted mean or the expected mean of 45.05, times that binomial or not times, but comma, that binomial standard deviation of 4.601. It will be the exact same calculation. Watch what's going to happen here. Let me zoom in a bit. First of all, here's the normal CDF that we did earlier. And here is the brand new normal CDF, 46.75, comma, some big number, comma, 45.05, which is the accepted mean, comma, now I'm actually going to type this, you know what, I'll just do 4.601. It'll give me an approximate number because I rounded it. But boom. But that was pretty darn close. It went out to 4 decimals on that one. But you can see it gives you the exact same answer. There's more than one way to handle these problems. There's absolutely more than one way to handle these problems. I want to make sure that you have everything at your disposal. Sometimes you will be faced with having to identify the binomial mean or binomial standard deviation. And if that is the case, this is a problem that you can do that on. Really messed up. In fact, let me jump to another multiple choice question, a different multiple choice question that's a bit later on that has similar properties to this. Yeah, I want to see what you guys can do with this. Now, again, do this any which way you need to do this one. Do this one any which way you need to do this one, but it's a similar type of problem. Suppose 56% of 8 to 12-year-olds expect to have a, quote, great life. In a simple random sample of 125 8 to 12-year-olds, what is the probability that between 50 and 60% will say they have a great life? You can handle this problem in either way, see what you can do with it, and I'll show you how you can type it in both ways later. Now, like I said, there's more than one way to do this problem. Absolutely more than one way. Let me kind of walk you through it. Well, first, let me give you the answer. Let me just prove whether or not you're correct or not. The answer should be D. The answer should be D. Now, notice something right here on the back of the card. First, on the back of the card, the first thing that this explanation does is it actually confirms the binomial successes and failures. But then it immediately goes back to a sampling distribution of p hat using all of those proportions. And this is the ultimate calculation that they end up putting in there. I'm going to show you both ways. The answer should be D. The answer should be 0.7279. Normal CDF. 0.50, 0.60, lower upper limit, 0.56, which is the accepted population mean, I guess, the standard deviation, which would be the square root of 0.56, 0.44 divided by 125. And that is the exact decimal that the answer says it is, and it's correct. It's absolutely correct. But it's not the only way that you could do it. You could also do this problem as a binomial, where I would convert everything to this binomial situation. This is going to be weird, but watch what I'm going to type in. First, I do 0.50 times 125. And then I would do 0.60 times 125. And then I would do 0.56 times 125. And then I would do the square root of 125 times 0.56 times 0.44. I believe this unmitigated mess, should give me the exact same decimal. All I did was convert everything to a binomial. N times P, square root NPQ, which they do give you on the AP test. They don't have the 2021 on there. That's why I keep going to 2019. But on that probability page right here, if I could zoom in on the left, they do give you a few binomial formulas that you can see right there. If X has a binomial distribution, they do give you the mu and the sigma right there. So you don't have to memorize them, obviously, but they do throw them on the formula sheet. Okay. Let's see where we can go from here. Ooh, let me jump into that one. That's a good one. Come on, you. I lost it. Haha. Okay, this is good. An inspection procedure at a manufacturing plant involves picking 3 items at random and then accepting the whole lot if at least 2 of the 3 items are in perfect condition. If in reality 84% of the whole lot are perfect, what is the probability that the lot will be accepted? You can't do normal here. The sample size is too small. You can't do normal here. Take a few minutes, see what you can get here. Okay. I'll show you what the correct answer is in a few moments. I want to walk you through something real quick, though. I told you that this thing was not normal, and I stand by that. I absolutely stand by that. Watch what happens when I attempt to do normal CDF here. The problem says, okay, what is the probability that at least 2 out of the 3 items are in perfect condition? 2/3, comma, big number. That's, 2/3 or more. Assuming, in reality, 84% with a standard deviation of 0.84 times 0.16 divided by a sample size of 3. That is not the answer. That is the farthest thing from the answer. This cannot be a normal CDF problem because the sample size is not large enough. It's a sample size of 3. No successes or failures being greater than 10 here. You can't do it. This is a binomial problem. And considering the fact that this is a binomial problem, I'm going to have to end up using, in this case, binomial CDF because they want at least 2 of the 3 items in perfect condition, meaning 2 or more. There are 3 items. There's an 84% chance of success. Now, they want 2 or more, meaning I'm going to type in a 1 because it will calculate the probability of getting 1 or less. And then if I just do 1 minus that, it gets me my actual correct answer. That is my actual correct answer. On the back of the card, it says that the answer was E. Now, on the back of the card, they actually did it in a different way. They did it in a completely, well, not a completely different way, but they did it with a different calculation that I'm going to show you. I'm just going to slide this up in a moment. On the back of the card, they actually used the definition of what a binomial is and how it's actually calculated using like combinations and stuff. You don't actually have to do that. You just use this, and it works just as fine. Probably even better. Let's jump. Not that one. Not that one. Ooh, not that one. No. Maybe another time for that one. You guys remember probability trees? Yeah. I don't want to do that today. I don't want to do that today. I would like to focus on something else. Oh, there we go. Heck yeah. A person has a 10% chance of winning the daily office lottery. What is the probability she wins on the 4th day? You can't calculate anything for this because they're actually wanting you to figure out, okay, what form of a calculation is needed for this. I'm going to let you make the decision before I talk about what this is. What type of problem is this? Clearly, it's a probability problem, but what type of problem is this? I'll give you a small hint. It is not binomial. This is not a binomial problem. What type of problem is it, though? Ooh, I can tell you what the correct answer is, but I won't show you what it is just yet. I won't show you what type of problem it is just yet. But the answer on the back of the card claims that the answer is D. And yes, the answer is D, by the way. But the question becomes why? Why? I got to get this piece of paper here. Here we go. Move this up, move this down. This is question number 14 on here. They say person has a 10% chance of winning. Probability of getting a first win on fourth day. The wording of that question, this is a geometric problem. This is geometric probability. This is absolutely geometric probability. Getting a first success on a certain trial. Unknown number of actual trials. There's no n value to speak of. It's getting that first success on day 4. Meaning that the person failed on days 1, 2, and 3 to win the office lottery. There's a couple different ways of handling this problem. But the probability of a geometric, in this case, the probability of a geometric success comes down to, well, which trial are they winning on? Well, there's the probability of success, but then you would fail on the previous trials. That's actually one of the formulas, I believe, that they don't give it to you actually on the test, but that's one of the formulas that we did for geometric. It's like, okay, well, I failed, and then I failed, and then I failed, and then I won. Or 0.90 cubed times 0.10, which is the answer for D, just in a different order. But that is the correct way to go about it. It's a geometric problem. I kind of show the card right here, zooming in, zooming in, zooming in, zooming in, zooming in. This is a geometric setting, and the probability of the 3 losses followed by a win is as follows. Sometimes they'll throw stuff at you like that just to mess with you. Just to mess with you. Oh, those problems. Let's see. Oh, that's a good one. Words, words, words. This is not a binomial. This is not a binomial, but probability definitely was something we needed to work on. There are 2 games involving flipping a fair coin. In the first game, you win a prize if you can throw between 45 and 55% heads. In the second game, you win if you can throw more than 60% heads. For each game, would you rather flip the coin 30 times or 300 times? And then they have your options. I'm going to give you a little time to read that, and then you make your choice. There's 2 ways of thinking about the problem. One is from a calculation point of view, and the other is from a logical point of view. the more the number of trials, the more the number of trials, the closer your sample proportion or your sample probability will approach 50-50 for flipping a coin. The less the number of trials, the more erratic or more varied the data will end up being. So in the first game, if you want to win a prize, but you have to hit between 45 and 55%, yes, please, I would like more trials in that first game. The more trials, the closer I'm going to get to 50-50. So I would rather do 300 times for the first game. But then as a result, I got to get more than 60% on the second game? Ugh. Yeah, if I do 300 trials, that's going to be way closer to 50-50. But if I do 30, there is a chance of getting a more erratic number. So that answer has got to be D. And you can see that right there. Now, if you were more analytical and you were like, I want to do the calculations for this. Okay, you can do the calculations for this. You absolutely can. Normal CDF, 0.45, 0.55, 0.50, the square root of 0.5 times 0.5 divided by 30. That's 30 trials, getting between 45 and 55%. There's 300 trials of getting between 45 and 55%. Heck yes, more trials, please. I have more of a chance of getting in those limits. It doubles my chances. More than doubles my chances. But then if I'm looking at 60% or more, 50% chance of success, square root, 0.5 to 0.5 divided by 30. This is getting 60% or more. I got about a 13.5% chance there. But if I do 300 trials, there's not much of a chance of that working out in my favor. Not really. Okay. Nah, I don't want to do that one. Skip. Oh, that's a good one. This one should be fairly straightforward and quick. I'm just going to let you read it and see what we think here. A mortgage company advertises that 85% of applications are approved. In a random sample of 30 applications, what is the expected number that will be turned down? Here we go. All right, sorry. My wife sent me a picture, and it was adorable. Anyway, 85% will get approved. Random sample, 30 applications. What is the expected number that will be turned down? Just for the sake of argument, chapow, the answer is B. The answer is B. Now, why is that? Well, B is technically a binomial calculation. B is looking at the number of trials times the percent chance, the probability of failure, which in this case is 15%. Again, it's one of those things where they don't actually give you the opportunity to calculate it. They just want to know how would you set that up. Down here, D, this would be the standard deviation or the expected standard deviation given 30 trials. This one right here, this would be the expected standard deviation if you were just dealing with proportions or a proportional distribution, something along those lines. I don't know what C would be. C is nothing. C would be, I guess, like variance of the binomial, but that's neither here nor there. There's some problems I like and some problems I don't. I picked these just as like, oh, this is perfect. Okay. Suppose, I'm going to have to zoom in a little bit on this. Suppose we have a random variable x where the probability associated with the value k, I'll zoom in right there, hold on, is, well, if you happen to remember the notation, we didn't spend that much time on it, but this is a combination of 12 ck, 12 combination k. It's a certain calculation for a binomial in your calculator. But they want to know, what is the mean of x? That's literally the question. What is the mean of x? Come on, focus. There it is, right there. The way that that is set up, they give you just enough information to be able to calculate the mean of x. And again, I want to emphasize, this is a binomial. This is a binomial. See if you can't make the guess here as to what this thing should be. Just for the sake of argument, it's not E. It's not E. Don't take the easy way out. It's not E. I'll show you what the answer is, and then I'm going to explain why. The answer is C. This is a binomial, as the card says right there. When you look in at this calculation that they're attempting to do for a binomial, when you look at this calculation right here, again, this combination, I don't know how that combination, I mean, I know, but you may not know how that calculation's done, but it doesn't matter. You can identify certain components of it. That 12 is representing the number of trials. That 12 is representing the value of n. K is representing the number of successes that they're looking to get. But that doesn't help me with the mean of x. If I want to do the mean of a binomial, it's just n times p. And if it is n times p, well, 12 is my n value. And according to this calculation, 0.34 is my probability of success, because I would have success in k of those trials, and I would have failure in the remaining trials. N times P, 12 times 0.34. Oh, can't see it. That is the calculation that they want. I have one more question that does not require any calculations. I have one more question that does not require calculations, but it is still a probability question technically. It's this one right here. A population is normally distributed with a mean of 58. Consider all samples of size 5. The variable x bar minus 58 over over square root of 5 has what? This one doesn't require calculations. This just requires a little bit of logic. Question. Do you have the population standard deviation? How do you know? They only give you S, which is the sample. It's not A. This is a T distribution. This is a T distribution. It's either B or C. What's my sample size? It's 5, which means America. The answer is C. The answer is C. It's a weird question. I love it so much, though. Okay. You have a minor due on Friday for chi-squared. We will continue a little bit with probability on Friday, but then I am going to give you something short on linear regression, but we'll get there when we get there. If you have my calculator, make sure you wipe that thing down and then put it back in the bag. Otherwise, that is the bell. Oh, I'm going to leave the chat open just for a few more moments in case you haven't left a comment yet. I see the ones that have so far. So if you would, please leave a comment. That'd be great. Thank you, too.